Hi. We are going to continue solving our dynamic programming contest. Of course, only in solving, because we were unable to solve all the problems during the contest time. It was 16 hours, but unfortunately at this moment I went to bed. So now. Still, it's not an excuse to not finish this contest. So let's look into this problem. Actually, let's create a whiteboard. So we have a problem. We have an array of size n, which is called S. Array of integers. And we have few queries. So first query is, we are given a segment LR, and we need to add an arithmetic progression to this array. The second type is to assign an arithmetic progression on a segment. Okay. And finally, we need to find the longest subsegment, the elements of which the longest subsegment of LR, the elements of which are arithmetic progression. Well, at first glance, it does not seem like a problem on dynamic programming. However, I immediately have an idea. So instead of looking at the initial array, let's take its difference array and look at it. Yeah, because in terms of difference array, it should be easier. And so we have an array, a1, a2, etc., an. So the first type of queries is that we have a segment and we need to add an arithmetic progression. So plus. Okay, actually, this is two separate things. Firstly, we add a constant, and we also add plus bi plus bi plus 1, so L, etc. plus br. And next thing is to assign this. Actually, instead of assigning an arithmetic progression, we can assign it to 0 and then use the previous query. Okay, so we need to add a constant, add plus bi, set to 0, and also we need to find the largest segment which is an arithmetic progression. Great. Do we need to find the length of it? Yeah, the length. So instead of that, let's consider the difference array. What happens here? So add a constant, it is simply add a number here and subtract it here. Okay, next. Okay, also instead of adding this on a segment, we can add it on a prefix. Yeah, so instead let's assume that here we had 0 and now we have here 0. Not 0, but the difference between 0 and the first element. Which is a0. So we need to add a constant on prefix. It is simply to add a constant here and subtract it here. Then adding this thing is simply well, it depends. It is to add like a lot of plus b's on a segment. Okay, and on a segment, we need to find the longest segment of equal numbers. Let's again take the difference array. So now we have the following. Well, actually, it is a problem. We have a problem here. It is quite hard to assign 0, of course. It's quite hard to assign 0. Since after we do it, something strange happens here. Yeah, what's the problem? The problem is that we need to immediately know. So we're taking the difference here between AI and AI plus 1. However, we don't know AI actually. We only know some strange statistics. So if we can fast find an element, then we can fast do everything else. Okay, so again, what do? We have a segment tree which consists of the following numbers. So it consists of 2a1 minus a0 minus a2, 2a3 minus a 2a2 minus a1 minus a3, 2a3 minus a2 minus a4, etc. 2an minus 2 minus an minus 1 minus an minus 3. So n minus 2 numbers, we store them. Also, let's just store, for a good measure, let's also store a0 and a1 explicitly. So we just know these numbers all the time. We know them. We can store them always. Okay, now we have several queries. So query number 1 is to make some number zeros. So we have a segment of values from from AL to AR, and we need to make all of them zeros. So all numbers which are from AL plus, so this is called C. Yeah? So all numbers from, and this is C0. This is C1, this is C2. This is C, etc. This is C n minus 2. Okay, if we do like this, then so first of all numbers from AL minus 2 to AR plus 1, they are not affected. So this and this not affected. So what do we have? C. So we also have CL minus 1, CL, CL plus 1, etc., CR minus 1, and CR. So let's see their definitions. For example, this is 2AL minus 1 minus AL minus 2 minus AL. We simply need to subtract. So now this becomes 0. So we need to add AL here. Secondly, what about this number? So this number is 2AL minus AL minus 1 minus AL plus 1. So actually we need to make it equal to okay, let's say it like this. We need to add AL plus 1 minus 2AL. Okay, this number is equal to 2CR minus CR. Sorry, I'm not correct. So actually it should be minus 3 here. Minus 3, they are not affected. However, minus 2 is also affected. Yeah, because it is equal to 2AL minus 1 minus AL minus AL minus 2. So this is added AL. This is equal to 2AL minus AL plus 1 minus AL minus 1. So this is added AL plus 1 minus 2AL. Okay, now all these numbers, let's see. All these numbers from here to here, they are just equal to 0. And to this number we need to add AR, and to this number we need to add AR minus 1 minus 2AR. Okay? So we need to do... Which things do we need to do? We need to assign 0 on a segment. We need to add some constants. The problem is we also need to calculate AL. We need to calculate AL, AL plus 1, AR minus 1, and AR. how do we do it? So, to understand that, let's firstly look at our numbers. So we have C0, C1, C2, C3, etc. Let's look at them. So this is 2A1 minus A0 minus A2. Actually, you know what? I think I don't like it. Instead, no, I don't like it. Instead, let's assume that, so our array, instead of A0 to AN minus 1, it is from A2 to AN plus 1. But also there are A0 which is always 0 and A1 which is always 1. Let's make this assumption. And after that, the formula for C is the same. Yeah, so we have C I is AI minus 2 AI plus 1 plus AI plus 2. This is the formula. This is what I think is correct. Okay, now let's look at sum from I equals 0 to j minus 1 of Ci, of Cj, of Ci, yeah. This is what? So first of all, it is A0 plus etc. plus, let's call, yeah, for now, let's say that Si is equal to A0 plus etc. plus AI minus 1. So sum of Ci from 0 to j minus 1 is, first of all, it is Sj minus 2 Sj plus 1. Notice that I ignore that A1 is not, A0 is not taken because it is always 0, as I said. And plus Sj plus 2. Okay, and after that, we can notice that this difference is Aj, and this minus Aj, and this difference is Aj plus 1. Okay, so this can be called Dj. After that, let's look at sum of Ti from I also from 0 to j minus 1. And this time, this is equal to what? So this is a1 minus a0 plus a2 minus a3 plus aj minus aj minus 1, and this is simply aj. Okay, so we can calculate sj. Okay, now let's rewrite this in terms of CIs. So let's swap these to summation signs. So k from 0 to j minus 2. Here we have ck times sum of I from k plus 1 to j minus 1. And here we have what do we have here? We have here 1. So here we have ck times j minus k minus 1. So what is it? Actually, we can rewrite it as sum from k equals 0 to j minus 2 minus kck minus plus j minus, actually let's write it as minus here, plus j minus 1 times sum from k equals 0 to j minus 2 ck, so which is simply d j minus 1. Well, so we need two things now. We need to calculate sum on a prefix, and we need to calculate this more strange sum on a prefix. So this is something that a segment tree is capable of. So let's do it. Also, so what does it look like now? So we need to assign 0 on a segment. We need to change some elements, add something to some elements. Also, we need to find the longest segment of zeros. This is pretty standard, I think. To do that, we need to find the longest prefix and the longest suffix on a segment. Okay. 3 seconds. So this seems enough. Now let's try and do it. Oh, also let's find out what is the maximum possible value. So at maximum we can add 1 million plus n times 1 million, n minus 1 times million. So it is 3 times 10 to the 11th power. So this is simply long. So we just need to store some longs. Okay. Let's implement this data structure. So again, what do we need? So first of all, we need to assign 0 on a segment. Let's write this function. Assign 0 from L to R. So to do that, we need a vector of bools, which says, do we need to push 0 into our children? So let's make a segment tree from top to bottom. This is called push 0. Okay. Actually, you know what? I think we can just have 2 regular segment trees. Okay. No, I don't want it to be like this. So let's just have VL so we have VL VL sum and VL index sum. Okay. So how do we assign 0? It should be easy. So let's make a recursive function. So what does it need? It needs number of vertex, the left side of this vertex, the right side of the vertex, and the left and the right sides of the segment. Actually, VB is not good because we have here VB. Okay, so left vertex and right vertex, and left segment and right segment. So if a vertex is to the left of the segment, then we return. If segment is to the left of the vertex, we also return. If the segment is inside of the vertex, then we need to push 0. How do we do it? We say that push 0 v equals true, and sum v is 0, and index sum v is 0. Okay, and return. Well, otherwise, what do we do otherwise? Let's write a new function, push. So actually push is easier. So if push 0 is, then push 0 is false, and we push into to our children, which are 2v plus 1 and 2v plus 2. Let's write in our function, which is called nullify, which nullifies the vertex. So first of all, if v is at least push 0.size, now we return, else we say that push 0 is true, sum v is 0, and index sum is also 0. Now we just nullify to our children, and here we need to nullify v. Okay, otherwise we need to just push v and go into our two children. So how do we go into our children? We assign 0 recursively into 2v plus 1. And to the right half. After that, we need to recalculate our own vertex. So this is done via recalc of v. So how do we recalculate a vertex? So quite easy. So we say that sum v is get sum of 2v plus 1 plus get sum of 2v plus 2. Actually, not like this. We need to ask if 2v plus 2 is at least sum.size, we don't do anything because it is too big. Otherwise, we say that sum v is sum 2v plus 1 plus sum 2v plus 2, and the index sum is same. And before that, it's okay to push, just in case. Okay, we can assign 0 now. And assign 0 here. is to assign 0 recursively in vertex 0 from 0 to n on a segment from L to R. Okay. Next query is to add a constant on a segment. So we also run add constant. What is that? Oh my god, it is something from the STL. So we need to add constant recursively from 0, 0, n L R val. Okay. How do we do it? So first of all, again, this is easier. Okay, here it gets trickier because we don't nullify if our segment is entirely inside the vertex. No, if our vertex is entirely... I did it incorrectly, so actually it's not like this. The vertex should be inside this segment. And the same here. So if the vertex R is entirely inside the segment, then we need to actually we never need to add a constant on a segment. We need to add to an element. So I was wrong. We need to add to an element. Okay, so if our element is outside of this segment, then we're of the vertex. Then we return. Otherwise, we need to do something. Actually, I believe what we need to do is we need to go to the left and to the right child. So if RV minus LV is at least 2, what we really need to do is to add constant recursively to 2 children. After that, we need to recalculate. And also we need to push, of course. We always need to push. And we need to recalculate V. Otherwise, it's trickier because we have a leaf. What do we do in a leaf? We need to add a constant to our leaf. How do we add a constant in our leaf? Okay, to add a constant in our relief, what do we need? So to sum, just this constant is added. But to index sum, rather than a constant, added number val times x, I guess. Okay, now we're capable of adding a constant. Now let's add an arithmetic progression. Ah, no, we don't need it. Yeah, we only need to assign 0 and assign and add a constant. What we really need to do is we need to find some statistics. So let's look again what we need. So this sum can be called ej minus 1. So we need to calculate on some prefix dj minus 1 and ej minus 1. And we can just let's write two functions. First of them just finds this pair. Yeah, so using PLL equals pair long. And we need to PLL find sum recursively. Again, we have a vertex, we have left and right bound of this vertex, and we have left and right bound of our segment. At first it's as here. So again, if we are outside of the segment, we return 0, 0. If we are outside of our segment, we return 0, 0. If we are entirely inside it, we return sum v and index sum v. And then we need to push. It's not const actually. It's not a const function. We need to push v. Okay, then we need to find sum recursively here and here and return it. So PLL ans left equals this, PLL ans right equals this, and we need to return ansl.f plus ansr.x and ansl.y plus ansr.y. And x and y, let's define. Okay. Now let's write a function which allows us to calculate an element. So long find a int x. So how do we calculate So we want to calculate aj, and we know that it is a prefix sum of di. This. So to calculate this prefix sum of di, we need to make this sum, which is this sum, which is this sum, which is this sum, which is simply minus ej minus 1 minus plus j minus 1 times dj minus 1. So we need the j minus 1 sum. Correct? So we need to find d and e, which is find sum recursively from vertex 0 to r to n, and the segment is from 0 to what? To j minus 1, I believe. And then we need to return x minus 1 times te dot x minus te dot y. Well, is that it? No, this is not the end, because we also need to find the longest segment of zeros. And in order to do that, we also need to store a longest prefix, longest suffix. Okay, let's call it really long. Longest 0 prefix, longest 0 suffix, and longest 0 segment. How do we do it? We need to also recalculate them in the mutating operations. So let's start with nullify. Nullify actually, it doesn't really mutate anything, but we need to do it in order for lazy propagation to work properly. So here we now will need to store in LV and RV. They are needed here, because here we will say that longest 0 prefix of V is RV minus LV. And the same for suffix and segment. Great. How do we push? So in push we also will need int LV and RV. Yeah, because here we need to give it LV and LV plus RV over 2. And here we need RV, LV plus RV dot over 2 and RV. Okay, this is nullify. Now recalculate. Recalculate is easy. We also need LV and RV. We need to push right away. And we need to recalculate these three things. Okay. So how do we calculate longest 0 prefix? It is, let's do like this. So initially, okay, I think we need to do like this. Longest 0 prefix of V is it true that sum V is 0? And the same in other two. Okay, assume that it is not true. Then we push. We calculate this and this. So what is the longest 0 prefix? It is the longest 0 prefix of 2v plus 1. And if this is equal to Let's also calculate mv, which is lv plus rv over 2. And if this is equal to mv minus lv, then we need to add the longest zero prefix of the other child. Okay, here we have it the other way. So longest zero suffix is longest zero suffix of 2v plus 2. And if this longest zero suffix is rv minus lv minus mv, we also need to add here the longest zero suffix of the left child. Finally, here it is the maximum of three things. First of all, it is longest zero segment of 2v plus 1. And of 2v plus 2. But also, we need to try here taking simply longest zero suffix of 2v plus 1 plus the longest zero prefix of 2v plus 2. Great, we have written this function recalc. Now, when we nullify, we also need LV and RV. Here we need LV and RV. Here we need LV and RV. Okay, how now do we calculate the longest zero segment? From L to R. Well, this is not very hard, I think. So we have a segment. It is divided into two. And if it is fully inside here or here, then it is recursive call. However, it might be also here. In this case, we need to take the longest prefix here, the longest suffix here, and we need to add them. So let's just write a function which finds all three things. Each finds the longest segment and the longest suffix and prefix of zeros. So pair of int and PII for longest zero segment recursive. And again, we have all sorts of arguments here. Great. Here we need to return longest zero segment recursive for 0, 0, n lr.x. well. Then it is pretty much the same. I know what I would like to do. Instead of these three arrays, yeah, and this strange function, I would really like to do something else. Let's make a structure which is called 0 segments. And it will have three numbers: prefix, suffix, and the segment. And here, instead of this abomination, we will have a vector of 0 segments. So what do we need here? We need here to combine them. How do we combine them? So we need a function 0 segments combine. What do we need here? We need 0 segments left length, and the same for the right part. Actually, it is static. So here we need right and the right part, right length. And we just need all the code from this thing. So first of all, okay, we need 0 segments ans, return ans. Okay, ans dot prefix is left dot prefix. But if left dot prefix equals left length, we need to add also right prefix. The same way, ans dot suffix is right dot suffix. But if right dot suffix is right length, then we also need to add left dot suffix. Finally, ans dot segment is maximum of three things. Actually, we need to include algorithm to use maximum. It's maximum of left dot segment, right dot segment, and left suffix plus right prefix. Great. Now we can write this function, combine. Okay, also, let's initialize it with something. Or not. No. Yes, so we can write here zero segment of V is constant RV minus LV. Okay, here we can also say that it is zero constant of this bool. Here we need to simply combine of two children. So first of all, left child, which is zero segment to V plus 1, and its length is MV minus LV. And then we need to take zero segment to V plus 2 and RV minus MV. So this is how we recalculate this part. Okay, assign zero recursive is easy. Of course, we have this thing in the recalculation procedure. Add constant is also fine. Find sum doesn't change anything. Long is zero segment recursive. Now this is interesting. This is getting interesting. Let's copy this, for example. So if they just do not intersect, we return how it's called, zero segments from a constant 0. And here we actually return zero segments. This, okay, here we need to return. We need to return our zero segment of V. And then we push, and then we need to combine our left and right answer. It's tricky. It's tricky because if this segment contains the middle, then we need to do it. But if it does not, then we don't. So let's do it somehow. Let's calculate MV equals LV plus RV over 2. So if MV okay, what we need to do is we need to calculate the length. So in the end, it will be definitely zero segments combine of ans L and ans R. However, we also need to give length L and length R. And we need to calculate them before we do it. How do we do it? So what is length L? It is actually just MV minus the left point of the segment, which is LS. So we need to write here, I believe, minimum of MV and LS. And here we need to subtract maximum of MV and RS minus MV. Okay, if done like this, we should definitely get everything right. Okay, so and here we need to return segment. We also need to initialize our structure, and to do that we need to write a constructor. Const vector of long. Actually, we can as well put here ints const vi v. So push 0 will be of size with size times 4. Then we actually know this function n, and we can apply it So sum will be of size 4 times n. Index sum will also be of n times 4. And zero segment will also be of size n times 4 and initialized with with what? For example, for now, let's initialize with constant 0. And here we need to build recursively from point 0, 0, n, and v. Actually, I would like it to be v, a, for example. So how do we build it recursively? Actually, everything regarding zero segment will be done by the function recalc. So we only need to say that sum. So first of all, if rv minus lv is at least 2, then first of all we build both children. Great. Otherwise, we need to build ourselves, so to say. So we need to say that sum v is ALV and index sum v is ALV times LV long clone. Yeah, after that, we need to recalculate zero segments and possibly our sum is incorrect. And to do that, we need to just recalculate VLVRV. So let's put the recalc function to the left of this and nullify to the left of this. It seems fine. So I think the structure is done. So the only error now is that we don't have any function main, unfortunately. Let's fix that. It does not know what iOS is because we also need to include iostream. Yeah, what do we do in solve tests? So we have done the multitest. Let's see what we need to read from the input. So first of all, of course, it is the array. This is the array. Okay, then we have the queries. The queries is like 5 numbers. It's a type. It is LRAB. So we need to read type L and R. Also, I would like 0 indexation, so we subtract 1 from L. And also, if type is not 3, we also need to read A and B. Okay, then we need to print the answer to the queries. Okay. How do we find the answer? We need to consider all queries. Actually, if q.type is 1, we do something, else type is 2, then we do something, and else type is 3, then we do something. Sorry. Okay. So the first query is to add an arithmetic progression on a segment. Well, let's think. So what do I do? What do I do? First of all, so I have numbers. First of all, I add 2 new numbers. So now this is like A0, A1, A2, etc. AN plus 1. So this is what I do. This is what I do. Then I need to calculate the new vector C, which is AI plus minus 2 AI plus 1 plus AI plus 2. So let's calculate this vector C. Yeah, this is the first thing that we need to do. So we say vi c of size n. So if I is at most 2, is at most... Okay, let's write a function. Get a. So if I is at most 1, we return 0, else return vi minus 2. So here ci is simply geta I minus 2 times geta I plus 1 plus geta I plus 2. After we've done it, we can easily create a segment tree on vector C. Great. Now we have a whole lot of different queries. Let's do the easiest one, which is find the longest zero segment. Yeah, so let's see what we are expecting. First of all, if the segment if of size at least 2, then definitely we just return the size of the segment. So if q dot r minus q dot l is at most 2, we need to push back the length of the segment. Yeah, otherwise we need to find... So we have now, after the changing of the perspective, it is from al plus 2 to ar plus 2, correct? From here to here. So which CIs are used there? CIs from al plus 2 to C. To C are exclusive, I think. Yeah, so because this number, if this is R, then this is R plus 2. So this looks here, and we don't need to look here. So from L plus 2 to R. Yeah, so else ans dot push back tree dot longest zero segment from q dot L plus 2 to q dot R. Great. Okay, we have 2 more queries. So the first query is to add an arithmetic progression. So first of all, let's add constant. Yeah, we need to add a constant on a segment. First of all, again, we added from al plus 2 to ar plus 2 exclusive. So what happens with CIs? So which of them actually change? Well, some of them. So we have CL, which is AL minus 2, AL plus 1 plus AL plus 2. And it changes. Yeah, we add here plus C. Then we have CL plus 1, which is AL plus 1 minus 2 AL plus 2 plus AL plus 3. And it depends. So if the segment consists only of this one number, then it is minus 2C. Otherwise, it is simply minus C. Okay, also we have C R minus 1. Not CR minus 1, but CR, which is AR minus 2 AR plus 1 plus AR plus 2. So this is usually minus C, but if this thing consists only of one element, that is if L is R minus 1, I think. Yeah, then it is minus 2C. And finally, C R plus 1 is simply plus C because we add C to this number. Okay, so in essence, we always add C to CL and CR plus 1. So 3 dot add constant to CL to what? Add constant. We need to write where and to what. So we add to L number A, correct? A, yes. We always add this constant to CR plus 1. Well, and actually, it's not very good because this consists of n elements. Yeah, this consists of n elements. So we cannot add something if this is too big. Actually, yeah, let's ignore the request if it is too big. So if x is at least n, we return. And in the same way, yeah, we return. So what have I done? So I need to add this and this, and also if the segment is of size 1, then I need to what? I need to add minus 2. I need to take this. Otherwise, I need to subtract QA from this number and from this number. Great. So this is how I add constant, but I also need to add what? So let's see. I have a segment from AL plus 2 to AR plus 2. And I need to add here A plus B times I minus L, so I minus L plus 2. Okay? I have already added A. Instead of this, let's just add BI. Let's just add BI, and then we will subtract minus B times L plus 2. Actually, we will do it immediately. So we will subtract b times l plus 2. Let me write a function, I think. Auto add constant on segment. So how do we add constants on segments? So as it turns out, we really need to add this constant. I need to do all of what is written here. Great. And here I simply need to add constant on segment QL, QR, A. And then, as I said, I also need to subtract b times l plus 2. So I write here this. Great. Now we need to add... Okay, we need to add bi on this segment. How do we add bi? Let's look again what happens. So we have a l plus 2, etc. a r plus 1, to which we have added bi. And here we did not add anything. Okay, what happens in this point? So first of all, we have CL. CL equals AL minus 2AL plus 1 plus AL plus 2. So to this thing, we have added B times L plus 2. Didn't we? Yeah. So we have added B L plus 2. Okay, this is simply a constant. Then we have C L plus 1. And here we have plus B minus 2BL plus 2, but plus BL plus 3. This is B times minus L minus 1. Okay. Then, starting with CL plus 2, nothing changes. Then it goes unchanging till CR minus 1. Then in point CR, we get AR minus 2AR plus 1 plus AR plus 2. Yeah, and here it is minus BR well, plus BR minus B minus 2BR plus 1, which is plus B times minus R minus 2. And finally, CR plus 1 here we have plus R plus 1. Okay, something like this. Let's do it. Actually, here we don't need to separate these cases, because as you see, if R minus L equals 1, then this simply does 2 times the same thing. I think let's just not separate it. So after we have added constant on segment, let's add progression on segment. So how do we add a progression on a segment? So in point L, we add BL plus 2. Actually, let's not slow it down. Let's not slow it down. Let's use here LLA and LLB. I don't want to slow it down. This is stupid to slow it down. Okay. Great. So we need to add B times L plus 2. Great. Here we need to add B times minus B times L plus 1. Here we need to subtract B times R plus 2. And here we need to add B times R plus 1. This is nice. Okay, we have added progression on a segment. Here we also need to add the very same progression on a segment, but before that we need to assign 0 on this segment. And this is trickier. So let's draw again what in our view is happening. So from AL plus 2 to AR minus 1, something should change. Okay, I have already calculated that, so let's recheck. Yeah. So here we will definitely need to consider 2 cases. Here we will definitely need to consider 2 cases. So first case is we simply need to add to eliminate one number. So AL. Okay, let's write some function, lambda. So we just need to write this function 0 segment. So if R minus L is 1, and else. There are 2 different cases. So if this difference is equal to 1, then it's not hard. We simply need to subtract to add regression on a segment. Yeah. So let's add regression on a segment from L to R. A is equal to the constant which we want to add, and B will be equal to 0. So which constant do we want to add? Actually, we just want to add 3 dot find A of L plus 2, I think, and minus this. We just want to subtract this number. That's it. However, usually L minus R, R minus L will be at least 2. In this case, several numbers change. So first of all, changes. So let me write it again, okay. So CL equals AL minus 2AL plus 1 plus AL plus 2. CL plus 1 equals AL plus 1 minus 2AL plus 2 plus AL plus 3, etc. CR equals AR minus 2AR plus 1 plus AR plus 2. CR plus 1 equals AR plus 1 minus 2AR plus 2 plus AR plus 3. Everything here just zeroes out. It vanishes. Okay, so here we need to... So this is getting 0. So we need to subtract AL plus 2. Here we need to add 2AL plus 2 and minus AL plus 3. Then here we need to add 2AR plus 1 minus AR, and here we need to subtract AR plus 1. That's it. This is for things that we need to do. So let's firstly calculate it. So AL plus 2 equals find A of, well, L plus 2. AL plus 3 is 3 dot find A of L plus 3. AR minus AR equals 3 dot find R, and AR plus 1 is 3 dot find AR plus 1. Okay. And then we need to add some constants. Yeah, to the numbers LL plus 1, RR plus 1. What? Why is this order? Why did I choose such an order? This is not good. Okay, so 3 add const. Minus AL plus 2. Here we use 2al plus 2 minus 2 minus al plus 3. Plus 2r plus 2ar plus 1 minus ar. And here we have minus ar plus 1. Great. Actually, we've done it. So far, 100% success. 1, 1 to 1? No. No, not 1, 1 to 1. How is it possible? Ah. Well, actually, it's not correct. So if I have 1, 0, I need to add 2 always. I need to always add 2 to my answers. Yeah? I need to always add 2 to my answers. Three, 3, 2, 3. A bit better. A bit better, but still very bad. Okay, I can just copy everything, so maybe at least something will be correct. No. Not a single thing is correct. Okay, I think I can make some easier queries. Let's start with the easiest thing possible. So it should be 10. It's 4 instead. Yeah, but we can check it. We can see why it is 4. Okay. There is something I don't like. Ah, no. There is nothing I don't like. Everything is fine. What? Ah, okay. So we have from 2 to 10, and here from 0 to 2, and here from 2 to 5. From 2 to 5, it should be answer should be 3. The answer should definitely be 3. Yeah, if you take from 2 to 5, the answer should be 3. 0 segment V is to 2. So build is incorrect. So this function build, which is such a tiny function, is incorrect. Ah, recalc. Recalc is incorrect. Maybe combine is incorrect. Can combine be incorrect? Combine can be incorrect. Okay, let's look into the function build. So I need the fourth vertex. Can I have the fourth vertex? So I build recursively these two boys. Okay, so 8 and 9. 8 is 0 for some reason. Yeah, so 8 is 0 for some reason. Actually, instead of this, I need to check something else. I need to check if RV minus LV is 1. So this is how you check that something is a leaf. Not the way I did, of course. And here we also not good. So we need to check that RV minus LV is 0. And in this case, we return. Okay, now it is 10, and now it is 5, 5 to 5. No, 5, 5 to 5 is bad. And almost everything here is bad. Let's make some nice changes. For example, okay, first of all, I want to apply this operation and see what happens. Yeah, so let's make again 10, 1. So it says, please add from 1 to 4, minus 1, minus 1. So first, let's add minus 1. So it becomes 0, 1, 2, 3. And then we also need to add minus 1 to minus each index. So it seems like this becomes 0, 1, 2. Ah, it's not 0, 1, 2, but 0, 0, 0, 0. Yeah. Also, let's look at the representation of this tree. So let's do something. Yes, so pi get all elements. Int v, int so pushed, first of all, equals pushed or push 0 v. So if pushed, okay, not if pushed, so if rv minus lv equals 1, then we need to so if pushed, we need to push back. Okay. R dot push back pushed 0 or a v. Yeah, some v. Else need to push back. Else we need to push back all elements recursive for v plus 1. And to the right part. Okay, and let's write another one function string. Let's write a function string to string, where we simply that answer plus equal if I answer plus equals this and answer plus equals vi to string. So here we can also write a function get all elements str, which returns to string of this function. Okay. Now we can debug everything. Okay, here it is 6. So actually we incorrectly added this array. Let's add this array correctly. So instead of that, let's jump. Let's jump here. I need to add a progression on a segment. So initially, yeah, if I look at tree dot get all elements. Okay, I need to sometimes run this function, it seems. So let's do it. So now it will have the address. Yeah, and we see actually what? Why it starts? Does it start with 1? And this -4 is strange. It should be exactly the same as vector c. What is happening? Why does it start with 1? Can somebody explain it to me? Ah, because we start with this array. Okay. Okay, maybe it's fine. So here we say 3 plus 1 minus 2 times 4. Okay, maybe yes. Okay, what happens here when you add progression on a segment? Let's write the array. And its difference function. So it is 1, 0, 0, 0, minus 4, 4, 0, 0, 0, minus 1. Okay, what happens next? Next we subtract 1. Then we subtract this thing. So what should it become? It now should become 1. No, not 1. 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. This is what it should look like. Let's see what are the regulations. So first of all, it says that in the point 0, we need to add minus 1. Okay. So it should become 0 here. And it did it. Okay, now to L plus 1, we need to add 0. So nothing happens. Yes, nothing happens. Then to point 4, we need to add 5. Okay, this is strange. Why do we add here 5? Well, this is because maybe I messed with this formula a bit. Let's look again. What do we need to add to CR? Yeah? So when we added a constant, yeah, yeah, so what did we add? That's right. We added A here, and we also added BR. Yes? Yes, we added A and we added BR. Here we subtracted. We also added A and we added BR plus 1. So in total, we added A minus 2A plus BR minus 2 BR plus 1, which is minus A plus B times, okay, minus A minus B times R plus 2. Minus A minus B times R plus 2. Is it what we see here? Yes, this is what we see here. So I don't understand why it is 5. But I think I should understand why it is 5, yeah? For some reason, I expected something else. Ah, yeah, it should be 1 here. Sorry, it should be 1. Yes, it is 1. Okay, I believe in it. So this is 1. And finally, this thing should make this 0 and yes. So now the longest segment, which consists of zeros, is this segment of length 4. But this thing still gives us 5. Okay, let's see why. Let's see why. So we have segment from 2 to 10 and numbers from 0 to 10. So we have ans L and ans R. So MV is 5. So from 2 to 5, the answer is prefix 2. Let's see what we have in reality. So from 0, from 2 to 5, the answer is prefix 2. Yes, it is. But on the suffix, for some reason, we have, so from 5 to 10, we have only segment 3, which is strange because we clearly have a prefix. Let's see why it happened. What? Ah, because 0 segment 2 is incorrect. Yeah, so 0 segment 2 is incorrect, which is not good. Let's see why it is incorrect. So we have added a progression on a segment, and in vertex 2 we needed to have a correct answer. So we have vertex 2. We need to add something in recursion. So at least it should know that it starts with 0. Yes? So sum v plus equals val, and val is -4. And I forgot to make a recalc. So actually actually. Actually, I needed to write here else, and only after that, I needed to make a recalc. So 5626. Okay, again, this is not correct. So clearly, we also have the incorrect function of assigning 0 in a segment. Okay, let's see what happens. It's okay. So, bad things happened when we applied this scenario. So, the segment didn't become 7. So we need from 5 to 10, assign -2, -2. Let's see what happens. We need from 5 to 10, apply -2, -2. Let's draw 0, 1, 2, 3, 4, 1, 2, 3, 4. Then, starting with 5, we need -2, -2. Ah, sorry. So from 5, it's actually from 7. Okay, let's look at this array. It's again 0, 0, 0, 0, 0, not 0, -2, 0, 0, 0, 0, 0. This is what it should become. Let's see what it actually becomes. It's 0, 0, 0, -2, but here it also has -1. So this number -8 did not change. Why? So it was 1 -1, and it's fine because these numbers were R is 10. R is, well, actually it's 12. So it, for some reason, it didn't change this number. Let's see why it did not change this number. Okay, this is interesting. Let's redo it. Let's calculate all these numbers. So they are AL2, AL3, AR, and AR1. 1255. Do we have here 1255? So L is 4. So we need the 6th element. 0, 1, 2, 3, 4, 5, 6 element. 1, 2, yeah. 7, 8. 10. 10 is 5. And 11 is 5. Okay, these numbers are all correct. But then, for some reason, it was unable to add well, I don't understand. It is completely in this segment 0. What? It is completely in the segment 0. Ah, I forgot to make the most important step, which was g dot assign 0 from L plus two to R. Okay, fine. Okay, this is correct, but this is very strange. It says 6554. It says 6554. Ah, I simply skipped this test, maybe. Maybe I simply skipped this test. 42341. Okay, 42351 would be correct. But here we have 42341. So far, only one incorrect answer. So this number. So it is statically incorrect. It was asked a static result and it was unable to find it. So from 5 to 9, it did not find all 5 numbers. Let's see why it happened. So I would like to look at this test separately from everything else. And even I would like to only ask this query. It says 4. It clearly says 4, which is not good. So somehow it says that the prefix is 2 and suffix is 3. I think which is not very good. So what does it say now? 1 1 1 2 2. Okay, this definitely means that prefix is incorrect. Yeah, if the length of this segment is okay, the length of this segment is 3. The length of this segment is 3. So why is it telling me that Okay, I don't believe in it. Ah, it's because 710, but here we have 6 9. Okay, the combining part is incorrect. The combining part is incorrect because because we actually need to take maximum of ls and lv, and here we need to take minimum of rs and rv. Yeah, and if at least one of the length is negative, we need to return the other segment. No, so now it's 5. Well, we can start submitting it. Not start, but try submitting it. Proc answer test. Test 6. Wrong answer, test 6. Unfortunately, we have to be realists. Wrong answer on test 1. Okay, maybe it somehow checks the year. I can remove it. But what? 5627. How is it incorrect? Ah, what? I submitted some other code, maybe. Oh no, I submitted some other code. Okay, sorry. Sorry for that. Actually, I don't want to do it. So this source file should be with the long template, not with the short one. Oh, it was a long journey. Yeah. Which is still not finished. Wow, the length of the clipboard history is impressive. I didn't expect it to be like that. So it's like backwards time lapse. Okay. Yeah, let's copy again all the input files. Okay, now we have 5, 6, 6, 2, 7, 5, 5, 10, 4, 2, 3, 5, 1, 6, 5, 5, 4, 2, 9. Runtime on test 1. Why? Because I don't return here. Yes, classic. I didn't return here. So wrong answer, test 6. Runtime error on test 9. Runtime error on test 9. Okay, so we need to write a stress, actually. Actually, we need to write a stress. It has been a long time since I last time wrote a stress, and now I need to write it again. Okay, so how do we write a stress? Let's make a struct test, which is vi initial and vl vector query queries. And then we make a test gen test, and then we ask a correct answer and fast answer. VI? I return VI, really? Ah, it's fine to return VI, yes. And if correct answer is not equal to fast answer, Then I need to print the test. So how do I do it? I print test. And I need to print test.v.size and test.r.size. Then I need to write all queries. If test.ri.tp is not free, I also need to print test.ri.a and test.ri.b. Then I need to print Ron and toString of past answer and write and toString of correct answer and return. Finally, I need to write this function find_unslow and gentest. So here I go through all queries. If q.type equals 1, then for int I equals, actually I need to say, I need to take VL w equals I need to take VL w of v.size and I need to copy. Yes. So here I need to go from q.l to q.r, and I need to say that wi plus equals qa plus qb times I minus ql. Else the same but assignment. Else say int current answer equals, actually let's say that answer dot pushback minimum of 2 and r dot q dot r minus q dot l, and int last progression equals 0, then I need to go through all numbers, and if wi minus wi minus 1 equals wi minus 1 minus wi minus 2 plus last prog, else last prog equals 0. Then I need to say that ans.back equals maximum of ans.back and last prog plus 2. And I need to write again test, of course. So how do I again test? I need to firstly generate n and q. Then I say that test.v.resize n, and I need to say that test.vi is, actually let's also say, for example, x equals 1. And here I say that it is UIT minus xx of RNG. And also q so I say that test.ri.tp is UID 13 RNG. Then I need to put here IL and R from how do I do it? 0 and minus 1. I think. Yeah, and then if they are greater, then I need to swap them. Finally, I need to increment this. And then fine, and also I need to assign A and B. Yeah. Just in case. Okay, something happens. Let's put here 222 because 111 is too easy. Still fine. Okay, 333. Okay, now it dies. Let's put here 1 first of all. Yeah, with 1 it also fails. What about 0? Does it fail with 0? It also fails with 0. Okay, now let's put here 2. Now let's put here 2. Now let's put here 1. So only with 2. Okay, let's look at the test. The test is zero zero zero, and the query is two queries of type 2. The two queries of type 2 kill everything. Okay, let's try to write it. So 3, 2, 0, 0, 0, 2, 0. Two zero three 2 1 3 0 0 and 2 2 3 0 0, I think. Let's ban the stress. And it still should fail. Yes, it did. Ah. Okay. Okay, maybe that way it would be better. Let's return our stress. Yeah, it seems better. Now let's return 333. And then 444. And then 20, 20, 20. Not 20, like 5, I think is better. But okay, it seems quite reasonable this time. Okay, I spent 17 minutes on this bug. It happens. My solution should not be very fast, but 3 seconds should be enough. It maybe is 1.5 seconds. I got this sort of feeling. Okay, only 1 second. Now let's look at the problem Z. Just a moment. I am writing to the author of this problem to add the statement which is not here. Okay, I have a problem. Just a moment. Okay, a festival in Munich, Munich, I don't know. Annually, there is a national festival. During the festival, there happen n events. Each event has a fixed and already defined timetable. And the timetable of n events is described by two sequences of length n, A and b. They satisfy the following requirements. Each integer from 1 to 2n, including is, occurs in A or B, and also AI is less than BI, and also AI is less than AI plus 1. So ith event starts at moment AI and ends at moment BI. The participants of the fest can choose any events in which they will participate, but they cannot participate in two events, the timetables for which overlap. Demit wants to participate in as many events as possible. In the previous year and before the previous year, he had been choosing the events to participate in by the following procedure. So if the ith event does not overlap with the timetable of other events which he has chosen, he will participate in ith event, otherwise he will not. So that is the greedy algorithm. However, after learning some informatics, Demit noticed that this algorithm does not always maximize the number of events in which he will participate. Starting this year, Demit will use an improved algorithm. And the improved algorithm, with it, Demit will be able to maximize the number of events in which he will participate. And he wants to find the number of cases in which the improved algorithm leads to greater number of events. So we will need to write a program which will, with given integers a and a big prime p, calculates the number of pairs of sequences A and B which describe the timetable n, for which this improved algorithm leads to a greater number of events. Since this answer can be very big, we need to print the residue of the answer modulo p. So essentially, we just need to look at this sequence an and understand how it works. Okay, now it seems like, sorry, I accidentally closed Codeforces. Okay, it's fine. Actually, I will participate in CodeTon, I think. Yes. Okay. Let's research this problem. So what do we have? We have a permutation and another permutation. No, it's like not two permutations. It's more of like a single permutation of size 2n. And we know that this is increasing and this is also increasing. Ah, no, this is increasing. So this is an object. There are 2n factorial possible objects, and we need to calculate how many of them are good. Okay. Okay, I think what we will need to do firstly is to calculate the total number of objects. So how many permutations among these ones in which this holds? So this is an interesting question, I think. We can try and calculate it for small numbers of n. Actually, to maximize, so why Dimit is unoptimal? Because when he chooses the events in this order from left to right, at some moment he can take an event which is too long and which actually overlaps with something. Actually, the optimal strategy is just to go in the same order but from right to left. So try an bn, then try an minus 1 bn minus 1, etc. And this works. This works well. Okay, let's calculate maybe something. So first of all, again, I want to calculate all possible schedules. So let's make a table. So n, all, and let's call it improved and not improved. So this is our table. Okay, if n equals 1, then there is only one timetable, 1, 2. And We have 2. Oh no, we have 1. Okay, improved equals I see. Or not. No, I don't see. Well, actually, the number of all permutations maybe we can calculate. So what we need to do? We need to divide all 2n numbers into several of type A and several of type B. And after we've done that, we know which of them are which. Yeah, so we know to divide them into 2 sets such that the first element of the first set is greater than the first element, or the first element of the first set is less than the first element of the second set. The same, third ones are the same, fourth ones are the same, etc. You need to find the number of ways to divide all objects in this way. So actually, if we consider any prefix of this sequence, in this prefix we will have AIs more or equal than BIs. And actually this is equivalent. So if I want to understand why AI is less than BI, let's take the prefix which ends at BI. We know that there are I, which ends right before AI. We know that there are exactly I minus 1 objects. So we know that there are at most BI minus 1, I minus 1 Bs. Then we add AI, and BI is somewhere to the right of it. So actually, this is just Catalan number, which is choose of 2n, choose n from 2n divided by n plus 1. So the total answer is just the number of proper parenthesis sequences. Okay, in terms of parenthesis sequences, what is the optimal answer and the greedy answer? Yeah, what is the optimal answer and what is the greedy answer? Actually, I stopped understanding why this is not optimal. BIs are not required to decrease. Yeah, the BIs can increase actually. Yeah, BIs can both increase or decrease. So not only do I have to divide, this set into A's and B's, but I also need to find a matching. And there might be a lot of matchings. So it's actually taking all proper sequences of parentheses, and after that, for each opening bracket, I need to find the closing one, which is after it. And there are a lot of ways to do that, because, for example, at least I can take just always opening and then immediately closing one. I can do this. This is also a correct way. Okay, actually, this means that I can calculate it. It shouldn't be hard. Yeah, because what do I do? So let's remove just the first pair. Let's just remove the first pair from the consideration. So I know that A1 is the minimum. A1 is the minimum among all of these numbers. So this is simply 1. I know that this is 1. B1 can be anything, just anything from 2 to n. It can be any number among these. And there is one-to-one correspondence from between, for example, let's assume that I choose 5 here. So this should be 5. Yeah, I can just remove both of them. I can move, so subtract 1 from these numbers and subtract 2 from these numbers. Now I have just 2n minus 2 elements, which I need to make into this structure of segments. So answer n is simply 2n minus 1 times answer n minus 1. So the answer is 2n minus 1 double factorial. So this is double factorial. Yes, that is 3, 15, 105, 945, etc. Then we need to find out how many of them are improved and how many are not. So let's start with the easy ones. If, for instance, when we have only one pair of numbers, each is not improved. Okay, now let's look at these tables. So 1, 2, 3, 4, 1, 3, 2, 4, 2, 4, and 1, 4, 2, 3. Yeah, so actually none of them is improved. Yeah, so if we have only 2 objects, it cannot be better than to take one of them, and if it's possible, then the other. So not improved is again 3. Let's go on. 15. There are many of them. Okay, actually we have the answer here. So for 3 it is 2, and for 4 it is 28. So if we subtract, here we have 13, and here we have 77. Interesting. Interesting and mysterious and eerie. Okay, what do we know about this sequence? Do we know something about this sequence? Again, so this is 1. We always take this 1 and b1. We always take them. Actually, this is already not always the best idea. Yeah, why? Because not only do we kill, so we just kill all A's, which are at most b1. So how can 1b1 be an optimal action? Okay, there are 2 ways we can lose. First way we can lose is after taking 1b1, our answer decreased. The second way we can lose is after taking 1b1, we did not decrease the answer. However, after taking 1b1, yeah, we have some residual structure, and in it, we don't take the optimal answer. So there are 2 ways to lose. Not take the optimal answer in the residual structure, or just reduce the answer. So an equals bn plus cn. Bn is a number of ways to reduce the answer. First step. During first step. And the cn is not take cn is have okay, let's write it. Not reduce the answer during the first step, but reduce it later. Okay, I need a pause. Okay, let's go on. I believe we need to start with B, because B is strictly more understandable than C. So how can we reduce the answer during the first step? So the answer would be optimal if we took the segments from right to left. Yes, so we have segment from 1 to be 1. And the optimal answer, if we take this segment, is to take the segments from right to left. So we take this segment, this segment, this segment, this segment. Okay, at some moment, the next segment that we want to take is somewhere here. So the question is, can we increase the answer? We can increase the answer if here we also can put one more segment. Well, actually, it depends on what happens here, I think. Because if this blue segment, for example, ends exactly here, maybe we just cannot put two segments here. So the fact that we reduce the answer definitely means that there is some sort of segment which is fully inside our segment. But this is not sufficient. We also need that if we take this leftmost segment, after that we can increase the answer. So the answer starting with this point should be less, strictly less, than the answer starting from this point. Like for instance, if we have like segment 1, 2, well, segment 1, 2 never decreases the answer. Maybe we need to calculate the number of ways to not reduce the answer. Yeah, maybe we just need to calculate the number of ways to not reduce the answer. So we need to find number of ways to choose these two arrays A and B, such that if we take these segments one by one, yeah, at some moment, we take the first one which intersects this segment, and it is not the only one that intersects it. So after that, we can also take one more segment. So how many ways to choose A and B such that this happens? So we take greedily these segments, and at some point, we can take one more here. Well, this is really hard because the structure of taking segments greedily, it is subtle. Hmm. Okay, so maybe we need to modify it a little bit. So again, we have, let's call it, for example, k. K is the answer if it starts with this point, 1. Okay, we also have L, which is what happens if you start from B1 plus 1. Okay, no. We won't consider working with arbitrary greedy algorithm, not non-effective greedy algorithm. So we can work with this when we go from right to left, but we cannot work with this. Yeah, because if we change something a little bit, for example, we take this segment, we can accidentally take after that this segment, and this is simply madness to work with it. So we will not. So start. Let's just say that we have LR answer at in some segment and RL answer in some segment. Okay, so we want to calculate the number of arrays in which are LR 1 to n does not equal to RL 1 to n. So this is what we want to calculate. Actually, this is less than RL. What I suggested is to take, so notice that this, yeah, is 1 plus R B1 plus 1 to n. And this is at most 1 plus RL B1 plus 1 to n. And this is at most this. So since we have here at least and at least, but in total it is greater, then at least one of them is strict. So either this is greater or this is greater. So this was my thought. However, sometimes they both are strict. So we need to understand what we do in this case. I suggested to put it somewhere. However, there are other ways to work with it. Also, sometimes 1b1 is the only possible optimal action, isn't it? Yeah, sometimes it is the only possible optimal action. Okay, can we calculate the number of ways? The number of pairs in which there is only one optimal sequence of actions. Can we do it? Actually, there might be. Yeah, there might be. So let's consider the sequence of actions. Some segment, some segment, some segment, some segment. Any other segment begins to be unoptimal. For example, there can be a segment like this. Yeah, if there is a segment like this, then it is better. Well, it's not better, but it is also fine to take it. Yeah, for example, there can be a segment like this, etc. So there can't be any segment which lies in this part or in this part. There can't be such segments. So each segment and there can't be any segment which lies here. What does it mean? Is it true that it is an equivalent condition? So if there are no such segments, then this is the only optimal answer. Yeah, I think it is true. Yeah, because let's take the other optimal answer, and let's consider the first segment, which is different. For example, this segment is the same, this is the same, and this is the first segment instead of which we have something else. So first of all, notice that if the segment started here, then it ended here. And if it started here, it also ended here. So actually, this segment ends to the right of this one. And then the next one ends to the right of this one. And then there is a problem because we cannot have a segment here. So yes, this is the case when we have only one optimal answer, is when we have some segments and then everything else, it just cannot lie inside these segments. So nothing can lie inside these segments. Okay. Understandable. Understandable but ugly, of course. Ugly, and I don't really like it. Okay, this one is easy actually. If I simply consider this one, this inequality, then this is very easy. Yeah, because I am simply asking, is it true that LR from B1 plus 1 to 2n is less than RL of B plus 1 to 2n? Yeah. So what do we know? We know that there are some segments. We know that there are some segments. So let's assume that, for example, there are k segments. Not k segments, but k numbers AI. K numbers AI. So what do we have? We have answer key. What do we need to do with this answer key? So we have some 2n minus 2k numbers. We need to do something with it. First of all, we need to choose also to the left of it. We also need to choose some k elements. And also we need to choose some more k elements. Some of them can be here and some of them can be here. Then we need to divide them into pairs somehow. Also, A1 should be paired with B1. Definitely. The rest of them can be divided in any way that I want, but all A's should be here. Okay. And that will result in an answer. So let's see how it looks like. So we have a key times. So let's say that we put L B's here. So L B's is put here. Put here. So the number of B's which I put here can be any from 0 to k minus 1. So I take AK times. I need to put L numbers here. So what is the number of ways to choose L numbers here? Number of ways is to take 2n minus 2k plus L and choose L among them. Okay. After that, I need to choose pairs. Okay, I also add 2k minus 2 minus L elements here. And I need to divide to find a pair, or to assign a pair for each of these numbers, which can be done in okay, in how many ways? It's not 2n minus 2k minus L, it's 2k minus 2 minus L. So times 2k minus 2 minus L times 2k minus 2 minus 3 minus L times etc. times 2k minus 1 minus 2L. After that, the rest of these numbers should be divided into pairs, which is simply 2k minus 3 minus 2L twice factorial. And that's actually it. So this is the answer. Maybe we need to simplify this. It's already not very bad, but we can simplify it. So, okay, this is 2n minus 2k plus L factorial over L factorial over 2n minus 2k factorial times 2k minus 2 minus L factorial divided by 2k minus 2 minus 2L factorial times 2k minus 3 minus 2L factorial, double factorial. Okay. So this is a function of n. Okay, this is a function of n and k, but actually if we need to change from some n to n plus 1, it is easily done. Yeah, because this factorial is easily... this is a strange thing. Yes? Yeah, there are actually k addends And for each of them, this is a bit different. But still, I can calculate all these pairs in... for each k it is different. Okay, I think we need to rewrite it as if L was k minus L. So let's say that M is... No, it doesn't make a lot of sense. No. Okay, actually it's fine. So what do we have? Essentially, what do we have? We have that. So let's call it B N K L. So this is sum of k equals 0 to n minus 1, ak times sum of l equals 0 to k minus 1, b nkl. So after that, we will have to calculate sum from k equals 0 to n, ak times sum of l equals 0 to k minus 1, of B n plus 1 KL. What does it change? So compared to the previous sum, what do we have? So B n plus 1 KL is B n KL times two n plus 1 minus 2k plus L times 2n plus 2 minus 2k plus L, and divided by 2n plus 1 minus 2k and 2n plus 2 minus 2k. So we multiply it by some number, which depends on all numbers n, k, l. But apart from that, so it depends. Actually, don't like how it depends. I'm really going to have a cubic time here, unfortunately. And in cubic time, I can calculate it without any problems. Okay, for now, let's calculate it in cubic time. Fine. So for now, we may assume that we can calculate this number. So now we need to calculate the number of situations in which RL 1 to n is greater than RL of is greater than 1 plus RL of B1 plus 1 to n. But actually this is equal to 1 plus LR of B1 plus 1 to n. Need to calculate the number of such situations. Okay, if we only want this equality, this is easy because it is again this thing, somehow something. But we also have this inequality, and by itself this inequality makes everything harder. Yeah, because we have 1, we have B1, and we need to make it that if I take this segment, then it is worse than I take I take this segment and everything here is worse than if I take optimally. Again, why does it happen? It happens because let's consider the optimal answer. If the optimal answer is larger, so I have the same number of segments here. I have some segments here. And then some segments which overlap with 1b1. How can we formulate it? We can formulate it that if we consider the leftmost segment here, yeah, for example, let it be BT, the place where the leftmost place where the segment ends. Then we need that starting here, the answer is greater than starting here. So we need that RL B1 plus 1 is strictly less than RL BT plus 1 to n. Yeah, let's prove it in both ways. So assume that we have our situation. In our situation, 1b1 is not the optimal way to choose a segment. Since it is not an optimal way to choose a segment, then there is this set of blue segments. Yeah, so I take them greedily. I actually also want this equality, which I still don't know how to ensure. But let's forget for now about this equality. So we have these segments, and at some point, this segment goes here in this optimal configuration. Note that since the optimal answer in R1P1 scenario is this one. So since this answer is strictly better, there is one more segment here. And this means that if I start from B1 plus 1, I get only S segments. But if I start from BT plus 1, I get S plus 1 segments. So this holds. Let's go the other way. Assume that this inequality is correct. So let's assume that this is S. Then this is at least S plus 1. And this means that actually 1B1 was not the optimal way to work. Instead of that, I could take ATBT and then this answer. Okay. So now we need to calculate the number of ways to firstly choose a segment here, the leftmost segment. Oh my god. To choose the leftmost segment, and then here to choose the remaining structure in such a way that this answer is less than this answer. Okay, maybe the way to go here is to work with this point. Yes, so I know that this point exists, and I need to work with it. I need to say that I calculate the number of configurations in which this point is in this place. What is this point? It is actually the leftmost point after taking the optimal answer. Okay, let's formulate our problem to make just answer with any asymptotics, just with any polynomial asymptotics. This is our aim. So if I allow any polynomial asymptotics, then, for example, I know this number S. Actually, you know what? You know what? I can calculate for any. So numbers A, B. I can calculate the number of arrays such that RL of 1 to n equals A, and LR 1 to n equals B. How do I do that? So let's fix that. I take one yeah, I take 1 B1, then I iterate over what happens here. Yeah, so I really know that LR here is now B minus 1. I know it. And then I need to iterate over what RL happens to be here. Yeah, for example, it is C. So here it is C. This means that I also need... Okay, not only does it equal to C, but I also know where it ends here. Yeah, so if I take the segments from right to left, I know where they end. Or do I need it? Yes, I kinda need it. I kinda need it. Okay, so what now do I have? Also, I can iterate over how many segments are here. So now I have the following. One, B1, some A's and B's. And since I know B1, yeah, this means that I know how many... I know also how many A's are here, so I also know how many B's are here. So I know how many B's are here. Okay, so the answer is C here. So right before this point, blue point. So the only thing that I need is that... Oh my god. Okay, no. It was bad. Instead, so I need a bijection. I need a bijection. So I have 1. I have B1. So I have taken this segment. Then I do everything else greedily. Let's now take from right to left also greedily. So I have this segment, I have this segment, I have this segment. Let's consider the first time when I go to the left part. So when I take this segment. If this is a 1b1, then I'm not interested, because this means that it does not actually mean that this was an optimal answer. Okay, maybe it was 1b1. Yeah, maybe it was 1b1. Almost surely not, but maybe it was 1b1. Actually, we can consider 2 cases. When it was 1b1 and then when it wasn't. Okay, now what? Now what? Okay, now again, let's calculate all polynomial solutions. This way I, for example, know the number of such segments. Now I know exactly where it ends here. So how can I reduce this problem to only this segment or only this segment? I can do it the following way. I can say that I want this element to go here, and that I want the number of ways in which the only optimal answer is one that starts here. So the only optimal answer is the one that starts here. Let's assume that I know how to calculate it. So if I have, so I guarantee that I know that the answer starts here. Then I can move this point anywhere here. And actually there are 2 cases, so this blue point might be here or it might be here. Actually, how do we differentiate between them? Okay, it doesn't matter for now. It doesn't matter for now. So I just need. So I have this construction. I have this construction here, where this is the last blue segment. Note that this should the only way should be with this point here, or else this is not the optimal segment. Okay, assume that I did it. Let's assume that I did it. This means that now I need to add the rest of the segments. And it helps that I know the value of P1. Actually, there are two cases. I should either actually note that since this answer is S, for example, then any other answer is less than S. So I expect that if I okay, for now let's assume that everything works. So there are two cases. Either I know that the blue segment's answer is equal for now to this answer, in this case all I need to do is to add segments in any way possible. So how can I do it? So what do I need to do? I already have this answer. I already have... Okay, there are a lot of cases actually. The first case is that this blue segment is here. I need to add new segments in such a way that Here, so first of all, first case, blue equals purple. Not purple, it's like pink. Pinkish red. Blue equals red. In this case, I need one more segment here, to the left of this blue one. Also, I want what? I just want some segments. So what are they supposed to look like? So a segment should be from here, for example, to here. What's not allowed? It is not allowed to have a segment If segments are not allowed to start here and end somewhere here. So this should be the segment with the leftmost start, with the rightmost start, which ends below this point. And in order to perform that, actually I need not this point, but this point. I need this point, actually. Okay, fine. So what do we need to do? So let's write what I need to iterate over. So first of all, I need to iterate over n. Then I need to iterate over b1. So I need to choose where I end my segment. After that, I need to choose where my leftmost blue segment ends. So I take them greedily here. I need to choose where it ends. Where, in which sense where? So I take the subsegment from b1 plus 1 to n, to 2n. I choose these optimal subsegments. And let's assume that I know this point. So this point is, let's call it x. So this point is called x, and I need to know x. Okay. Now there are two cases. If the optimal answer here, not optimal, but LR answer, is equal to s or less than s, so both cases are possible. For example, let's assume that it is equal to s. Okay, no, easier. Let's assume that this is less than s. So I chose the right part so that it is not only x I need to know, I also need to know a's in left half. So also I know number of a's in the left half. So assume that I know the number of a's in the left half. And since I know b1, I also know the number of b's in the left half and both numbers in the right half. So okay, what do we need to iterate over? we need here to iterate over the following. We need to so first of all, so this is called left half. This is called right half. And we know how many segments there are of this type. Yeah, of this type. So first of all, let's notice that so we already know anything which is strictly here, so we have only two types of segments now, which look like this and which look like this. We need to find the number of ways to add them now. So let's say that we have I inner segments and O outer segments. No, I don't like the letter O. Let's say that we need J outer segments. So also there are two cases. There are cases if LR equals S and less than S. So let's now consider the case when LR is less than S. So the answer is already unoptimal. We already know that starting from here we got an non-optimal answer. In this case we just need to do anything. We just need to do anything we want. So how do we do anything we want? We need to construct I inner segments and J outer segments in any possible way. How can it be done? Not very hard. Not very hard. To do that, first of all, we need to choose to put here somehow J points. So this is among n minus b1. We need to choose J points. After that, we need to make pairs with the left points. So it can be done in b1 factorial over b1 minus j factorial. Number of ways. After that, the remaining numbers here, b1 minus j, should be divided into pairs. And there are b1 minus j minus 1 double factorial ways to do it. Okay. And that's it? That's actually it? No, that's not really it. Because we used this thing. So we need to somehow calculate the number of ways to make take some points. So is it important for me in this case to know where this point is? I don't think so. I think it doesn't matter where this point lies. I think it doesn't matter where this point lies. So in this case, it doesn't matter. So I only need to know. So this does not matter. N cubed in this case is enough. So I only need to know. Even number of segments is not interested. Is not interesting. I don't need to know the number of segments. The number of segments is not important. Important is this point in the second case. Yeah, because in the second case, the greedy answer is equal to the optimal answer. And that means that I need to somehow now consider only cases in which I do something optimal. Okay, let's think how it works. Let's think how it works. So I already have some answer in the right part. I need to add something to the left, and I need to intertwine something here in a way that the answer to the left of x is at least 2. So to the left of x, there are at least 2 different segments. Actually, it shouldn't be hard. So how do I understand that the answer is at least x? Yeah. How do I understand that the answer is at least x? This simply means that so what is converse actually? What is converse? So how can it be that okay, the converse is that any 2 segments intersect. How is it possible that any 2 segments intersect? Actually, the fact that any 2 segments intersect simply means that I firstly have only opening brackets and then only closing brackets. Because if I have some opening, some closing, and then some opening, then I have 2 different segments. Yes, so among segments which lie to the left of point x, it's only opening and then only closing segments. And the number of ways to do it can be easily calculated. Wow, it's actually crazy. So, okay, if I want to solve with any asymptotics, with just any asymptotics, yeah, then here I can say so. Again, as I said, Okay, in theory, we know how to solve it in very slowly. So again, as I said, so we have here a point x. I can also choose the number of segments which go like this. So to the right of this point. Let's remove them. So everything else. So I need to calculate the number of ways to choose segments such that here the answer is at least 2. Instead of that, let's calculate the number of ways in which the answer is 1. So first of all, I calculate these segments. Then I need to only take the opening parenthesis and then only the closing parenthesis. So there is just a factorial ways to make the matching after that. So I will not implement this because I don't see any reason. So it can be useful maybe for the stress. But none other than that. Okay, maybe we can look how a prefix of this answer looks like. Let's consider a prefix. What do we know about the prefix? In the prefix, there are some segments and also there are some points in which a segment started, but it never ended. We had some points in which a prefix started but never ended. So what is the result of, instead of the RL algorithm, let's consider LR algorithm, so from left to right. But each time we take not the leftmost starting point available, but the leftmost right starting point available. So let's call them LR and opt. These are two algorithms. So if I run both of them at this starting thing, what can happen? So if at some point there is a prefix such that LR let me think. If there is a prefix such that LR in this prefix found n segments, and before this point, including opt found n+1 segments. In this case, I can immediately say that in the end, opt will be more optimal than LR. However, if opt found n+1 segment, but this segment went something like here, it doesn't mean that opt will be necessarily more optimal. So let's not consider it by now. For now. Okay, how? Let's assume that after the segment, there is a fake opening segment, or opening point. Will we do it? Okay, let's do it. In this case, LR algorithm will find several segments and some point, maybe one of these, or maybe this if it's impossible to choose this one. What does opt choose? The opt algorithm chooses segments with leftmost right ends. And when does it end? It ends when there are no more available right ends. So it ends when all left points here are black dots. Yeah, so the blue one ends with some black dot, and the green one ends with some segment which is to the left of some black dot. So what can we say here? For example, the optimum algorithm found this, this, and this. When can we say that it is definitely lost? It is definitely lost if the LR algorithm found two segments, including the black dot segment, yeah, because it ended to the right of us, but found less than we found. Okay, what about this case? Yeah, we found more, but we ended to the right. Ah, I see. If the black dot is to the right of our green segment, then we also can say that it is unoptimal. So the only way is if the number of green segments is less than the number of blue segments plus dot. Okay, let's count the number of blue segments excluding dot. In this case, green is definitely at least blue. So we can say that green wins if number of green segments is greater than the number of blue segments. And also the blue dot is to the right of our rightmost green point. If in this case we can say that definitely green won. So green lost for now, blue did not lose if their number is equal, or their number is not equal, but blue point is to the left of this segment. How is it possibly better? For example, we chose this one, and this one. How can it be? Yeah, so there is a green point here. Maybe it ends in the end. But we can take this segment. Yes. So again, our current state is a segment of points in which some are called big black points, some of them are segments, and also we know either that opt is greater than RL and point of RL is to the right to rightmost point of the opt. This is called case 1, or case 2 is otherwise. So what happens when we add one more point? There are two cases. Either it is an opening segment, and in this case almost nothing happens. Sometimes it is now RL, so RL here, RL ended in this point, but now RL ends in this point because it is a side, but nothing else changes. Opt does not change, RL does not change, optimality does not change. Or it can be a closing segment. In this case, there was some big black point here, and now it becomes a segment. And actually it is very bad. It is very bad. So no, it's not very bad. It's not very bad. Let me explain why. So for RL, actually everything is simple. So if this was the chosen point, then now we add this segment, and now this is the chosen point. Otherwise, nothing changes. Let's look at the opt solution. So we had some segments. Actually, we always chose the leftmost right end. And now we added a segment in which this is right end. So this is the rightmost possible end. This means that we don't want this segment until the very end. And this means that if this left end is to the left, is to the right of opt, then we connect them and it is added to the opt. But if not, then not. So how can we classify it? So again, we have a segment, and in this segment we have the number of active points, the number of active left starts, left parentheses. So it's like dp AB in first A parenthesis exactly B non-closed opening. Okay, this is actually not that bad. So again, when we have an open parenthesis, something changes. So again, we have several dynamics. Let's call it MK. So A MK equals opt already 1. This is the first case. The second case, BMK, is opt is greater than RL, but not 1. CMK equals opt equals RL for now. So let's see how the transition happens. Transitions. So again, let's look at the first transition, first type of transition. Okay, first of all, opening bracket does not change anything. It's kind of easy. Also, closing bracket. Okay, in case A, yeah, if we come somewhere from case A, it's always case A. So it's also not interesting. A is not interesting. Okay, let's assume that we had some state B. So opt was better than RL, but not 1. What does it mean? So for example, we have 3 segments, and RL only has two segments. For example, this one and this one. However, they started here, and this means that they still did not lose. What happens if we have a closing bracket here? There are cases. It could pair up with this point, or it could pair up with anything else. Also, there is a question. So when we look at this opt, it is interesting how many points are here actually. This is what interests us. We want to know how many points are here to the right of the opt. Okay, for now I still like this dynamic, so let's make a cubic dynamic. Let's make a cubic dynamic actually. So A M K L equals what? Equals that there is some opt answer, and for this point, yeah, there are k dots to the left of it and L dots to the right of it. So this is our dynamic. And still B is as I said, and C is as I said. Okay, now let's recalculate everything that happens afterwards. So if we add, so I want to calculate A M plus 1 K A M K L, for example. Let's calculate A M K L B M K L and C M K L. Let's go. So first of all, we could start from A M minus 1 K and L minus 1. So if we add after that a new open parenthesis, then it simply goes here. Actually, nothing changes. Always nothing changes. Do I get it right that simply nothing changes? I think nothing changes, yes. So here I can write that it is equal to A M minus 1 K L minus 1. Here I can write that it's B M minus 1 K L minus 1. And here I can say that it is C M minus 1 K L minus 1. Let's go on. What also can happen? So let's look at our opt. It can be closing parentheses. So first of all, if we have this, for example, and it is a closing parenthesis, or this, and this is a closing parenthesis, this doesn't matter. We already lost. Nothing can change the result. So we simply can say that plus L plus 1 A M minus 1 K L plus 1 plus K plus 1 A M minus 1 k plus 1 L. Okay. So if we started with already lost position, we couldn't win. Okay, now let's look at the situation when we started in B, for example. B or this B. So what does this mean? This means that opt is greater than RL, but not 1. So opt is greater than RL, but not 1. This means that active point is somewhere here. Let's start with this one. So in this case, actually we immediately lose. Because this case means that we add a new segment like this. Sorry. A new segment like this. And now opt is much better than RL. So we can write plus L plus 1, B, M minus 1, K, L plus 1. Great. What about this case? This case has two subcases. We either pair it up with this element or with something else. Okay, if we paired up with something else, then in both solutions nothing changed. But if we paired up with exactly this thing, then it becomes a C, because now opt equals LR. So we can write it like this. So plus B M minus 1 K plus 1 L times K, and here we can write plus B M minus 1 K plus 1 L. Okay, let's go on. So now let's assume that we started with C, so the number of segments is equal. Now we have some closing parentheses. Now it's getting interesting. And now it is getting interesting. So closing parentheses paired up with something to the left or to the right of green. Again, if it was to the left of green, then it doesn't matter. It simply doesn't matter. How can I write it? Let me write it like... How can I write it? Let me think. So nothing changed. So I simply have C M minus 1 K plus 1 L times K plus 1. Nothing changed. Okay, what else could happen? Also, I could pair up with this point. In this case, both of them are just increased by 1, and they're still equal. So also there is one way how it could happen like this. Finally, there is a case when I pair it up with something like this. Then now we go to the case B, because opt is greater, but still opt did not win. We can write it like C M minus 1 k l k, I said l plus 1 times l. Okay, this is our qubit dynamics. It can be calculated in cubic time, and in the end we get a and 0, 0, which interests us. Let's try and implement this, and then we will think how we can optimize it. It will be our find dance slow. Struct test. Solve test. So we only need to read N and P, yeah? Okay. We will need a dynamic of size what? Okay, let's say that orta what? Orta create empty, or I don't like it. Yeah, I don't like it actually. So let's just say we have VVI vector VI. Okay, so for in how do I want it? I want it layer by layer. So initially I have layer A0, which only consists of what? Let it be dp nm and dq. So in dp there will also be the optimal the current answer, and in the end we will say that return dp n 0, 0. However, what? However, we will make n to n recalculations. So also we need the initial state. The initial state is only we can have nothing. So the answers are equal. So let us make these arrays A, B, C. And pref A, pref B, pref C. And we need to calculate the number of things where A lost, so we need A00. Now we need to recalculate A, B, and C. Okay, let's... Mm-hmm. So... Actually, I only want I and J to be the same parity as ether. So here I need to say like ether plus I and 1. Something like this, if correct. So what I need to say here? I need to recalculate A, B, and C. And this is not hard because I already calculated the exact formula. So I need to say get reva of KL minus 1, IJ minus 1. Actually, I want KL now because everything is written in terms of K and L. KL minus 1 plus also I need a product And there are 4 things. Okay, let there be 3 things. So here I want product p plus 1 and a. And here I want to have sum of 2 products. Product of 2 sums. A product of L plus 1 and sum. A and B. Okay. Now what about B? B is sum of 3 addends. Okay, and finally C. C is very similar to this. Get pref C KL minus 1, product of... no, it's more similar to A. Wait, no products? Okay, whatever. Whatever. If there are errors, I will notice them the hard way, unfortunately. Okay, we are done actually. It's what we needed. Actually, I can also add 1 and 2, for which the answer is zeros. And as well, I think Actually, if I run it now, it will always be zeros because I didn't make any initialization. So actually I need to write A0 C00 is 1. Okay, now we at least see something. Something incorrect. Well, I think we need to understand why the answer is 2 here in order to get some answer. We need to understand why the answer is 2. So, okay, m equals 0. If m equals 0, then there is not much happening. We have nothing, and so the answer... we need 3 tables. We need tables A, B, and C. A, B, and C. One, zero, zero. Okay, now we have m equals 1. The only way it can work is it is an opening bracket. Actually, I feel like it will take a lot of time since I need to work for n equals 3 or 4. 3. No, 3 is kind of fine. It's still a lot of time. But I should be able to do it. So this is never true. Nothing could happen here. Could have happened here. And here we always have exactly one opening thing, and it is after the last opt segment. So it is here. Nothing could happen but this. Let's go on. M equals 2. Now we have 3 by 3 tables. I can copy. I can copy everything. Are you serious? I copied it. I press Ctrl C, Ctrl V. Yeah, now this time you work. Again, A, B, C. So I'm still sure that RL could not theoretically lose. It is impossible for RL to lose at this point. So no zeros here. It is also impossible for RL to have less than opt. There are simply 2 cases. Either they both are in touch, or they are both not. Okay, if they are both in touch, So for the both the segment, so there was an active point and it was connected with the next point. In this case, they're both equal and there are no active points. So it looks like this. Or they both now have 2 active points. So like this. Oh, like this. Yeah. Okay. M equals 3. We're going to do it till M equals 6, so I'm a bit afraid, to be honest. Why? I pressed Ctrl C. Why you cannot simply work? A, B, C. So now we have just 2 possible situations before that. One of them is like this, and the other one is like this. Let's consider all of them. First of all, we could have this thing. This would result in having 3 points. Another thing is like this, resulting in one point to the left of the opt. So this one. Also, we could have this thing. This results in opt being greater than RL, but still RL has an active point to the left of the right endpoint of opt, which means this one. Okay, let's look here now. We can only have an active point here. That would mean that we have one active point to the right of opt. So this one. That's it. Now the rest of the table is filled with zeros. So I think that what we need to do is to check that for now the tables are correct. Yeah, so we have A, B, C. I want starting with 3, I think. Okay, now A should be only zeros, and it is, and B should be only zeros, and it is, and C should be not all zeros, but it should be 0, 1, 0, 0, 0, 0, 0, 0. Yes. Okay, next case. A should be still all zeros. B should be all zeros. And C should be 1 0 1 0 0 0. Okay, then we look at the next situation. The next situation. And we need to have here the following. So A is still only zeros. B is zeros, then 1, and then a lot of zeros. Ah, here it is. For some reason, we have it here. So it thinks that when we add this segment, when we have this segment, yeah, I know what happened. So actually, it's not right. What is that case? That case is this one. Actually, yeah, we need to reconsider everything when this was a closing bracket. So we need to reconsider everything when it was L plus 1 and it got to L. Why? Because actually it did not get to L. If we had an opt answer, and then we have something like this, actually it goes to 0. Every time when we had L plus 1 and now it's L, it should go to 0. Why? Because actually it transferred. So now all these active points are to the left of the opt. All these active points are to the left of the opt. Okay, so actually it was a very rapid transfer. So what do we do? What do we do? Now, so now it is, we have to take sum of all possible how to write it. First of all, it should be true that L equals 0. Then we need to sum over all possible L prime from 1 to K, C M minus 1, K minus K plus 1 minus K from 0 to K minus 1. Or from 0 to k. Yeah, I think from 0 to k. So here we have k minus L prime plus 1 times L prime. Okay, here. Actually, maybe in A it does not matter a lot. I think in here it does not matter a lot. So in A we are allowed to not fix it. We only need to fix it in we also, I think, are allowed to not fix it here. So where do we need to fix it? We only need to fix it here. So again, here we need to say that L equals 0 times sum of L prime from 0 to k, Cm minus 1, k, L prime, not k, but k minus L prime plus 1. Okay, let's do it. Let's do it. So if L equals 0, then we need to go from L prime for L prime from 0 to k. And we need to say that BKL is sum of BKL and C product of L prime and get prev C of k minus L prime plus 1. Instead of that, here we need to remove this. I need to remove this. I need to remove this and this. After that, in C, I also need to fix it. So this last addend should be removed. Get prev C, k, L plus 1 should be removed. Instead of that, I need to say that CKL is sum, CKL and product of L prime, not a product actually of L prime, but simply k minus L prime plus 1. Still 1. And now it's worse. Okay, now it is correct. Unfortunately, still we get an incorrect answer. Okay, it seems that we need to look at m equals 4. Okay, so what do we have? What do we have? We have several cases. Several cases. Why can't you copy what I even pressed Ctrl C several times, not just one. I pressed it several times. Why are you unable to perform an easiest task? To copy something. Actually, I don't need the fourth column. I don't need the fourth column. It should be zeros. Okay, I even will fix it. I don't need the fourth column. Can I remove it? No, if I do like this, all table is gone. The whole table is gone. Why is it? Why can't you copy something? This is ridiculous. Okay. ABC. So let's see which configurations are possible. We could start with what? Okay, what is this one? It should be the easiest. This one is I have active point, then this segment. Okay, we can either have an opening segment, which would lead to this one, or this can be the closing point for this segment, in which case they are equal. And there are no points at all. So this one. Okay, let's go on. The second case is, for example, this one. Can you see my concept? So I'm interested in this one. In this one. So what does it mean? It means that we have I think, this picture. So we have a segment and we have this active point. Then if we have an opening, then now we have two active segments and two active points. And this is here. Or we can have the closing parenthesis. And that means that we do not have any active segments. That means that we finish here. Okay, let's go on. The next case is when we have a segment like what? Like this. So this is an active point. It is to the right of our segment. So if we have an opening here, then it becomes 2. So I think it goes here. But if it is closing, then it adds to both of them, and we get 2 segments like this, and now it is 3. Finally, when we have 3 opening segments, and we cannot have another one opening, so we can only have closing. So if it closes this one, then now it is like this. We have equal state, and we have 2 closing segments. However, if it closes, for example, this one or this one, then we have this state. No, 2 here. We have this state. The rest of items are zeros. Let's see what we actually have. So this was the previous state. Now let's move on. So A's. A should be all zeros. A's are all zeros. What about B's? B's are correct. Finally, C's. 3, 0, 1, 0, 1. 1, 0, zeros. Well, this is correct. Okay, to avoid my irritation, I will copy this And then I will copy this. Oh yes, and this time it copied it well. I even don't know what to think. I even don't know what to think. What did you do and why? Ah. Oh my god. Excellent. Well, let's move on. Okay, we have two cases when we see what do we see? So we have some optimal segment. We have 2 points here. The first of them is actually one of them, but we know that the first of them is the active point. So we definitely have a closing point. And either it closes this point, in which case we go here, or it closes this point, in which case we go here. Then we have the case when we have a segment and active points are this one and this one. We cannot have opening parentheses, so we only can have closing one. And when it closes, it either closes this one, yeah, and in this case we actually immediately lose. Or it closes this one, and in this case it is this case. No, yeah, this is this case. Okay, now we have a lot of cases in the right part of the board. Starting with just 3 of nothing. In this case, we can only have an opening bracket. And it is after everything, so we have here 4. Next, we have the case when we have... So this is the optimal segments, and we have two active points. Then we cannot have an opening, so we have to have a closing, and it closes either this one, in which case we go here, or it closes this one, in which case we go here. Then we also have the case when we have such and such point. Then we also can have closing parenthesis, and if it closes like this, then it is this. Sorry. Or it pairs up like this, and then nothing changes for nobody. I guess it's 5 here. Finally, we can have the case when there is an optimal segment, but both active points are to the left of its right end. Then the new closing segment will either go like this. However it goes, actually it is impossible. What? How can it be? How can it be that both active points both active points are here, and actually our active point which we chose is here, RL. So nothing could change at all. We just destroy one active point and that's it. So it should become 6 here and nothing more. Well, let's see what happened. What actually happened. Well, I don't like this table. This table looks like everything. This table looks like it's really a 1. So the answer should be 1. It says that here we have what? Here we have a 1? Maybe. I don't care when about this. Yeah, whatever. I don't care about that items. Okay. Clearly we have some problem. So we need to understand why the answer is 2 rather than 1, because I don't understand. I don't understand why the answer is 2. Okay, let's see. So actually, let's draw a table. Yeah. So what gave RL algorithm and what gave the opt algorithm? So the RL algorithm could give 0, 1, 2, or 3, and the opt could give 0, 1, 2, or 3. First of all, we immediately know that optimum is at least RL. So if opt is smaller than RL, it is impossible. So this is impossible, this is impossible, and this is impossible. Also, they cannot give zeros at all. Zeros are impossible. Okay, for 1, 1, Yeah, in total we have 15. We need to somehow distribute 15 points here. So the only way that both answers are ones, that optimal answer is 1 actually, is when it is split into halves, and here we only have opening, and here we only have closing. How many ways to do that? Well, there are 6. So here we have 6. Can it be that RL equals 1, but opt is greater than 1? I think yes. So first thing first, if we have something like this, yeah, actually there are a lot of ways to do that. Let's draw all of them. Yeah, first of all, if we have something like this, then actually RL will be 2, because here we'll have something like this, and it will find another pair. Ah, we can immediately find the answer 3, 3. It is like this. 1. And actually, if optimum is 3, then RL is also 3. So here we have 0 and 0. Okay. Now let's look at the case when RL is 1, but opt is 2. So first of all, it is this. And we can have this and this. But also it is possible that we have this pair, but optimally we can have this pair and this pair. Okay, I believe that answer is 2. However, somehow we did not see one of them. Let's look into our tables, and we will maybe understand how it goes. So let's start with this one. Let's start with this one. So we start with C00. C00. Then we have an opening bracket. So this becomes C01. Then we have another one opening bracket, and we get C02. Then we have this bracket closing, and now it is actually B 1 0. Then we have this closing. No, this is not optimal. This does not. This is not true. This is not what I need, because here the greedy answer is also 2. Actually, instead of that, I need not this, but I think this. Okay, this time this is fine. Let's see. So now again we have C00, then C01, then B10, then B11, then this thing closes. Yeah, this thing closes. And when this thing closes, yeah, it becomes bad for us. It is immediately A. Yeah, it is A. A what? For instance, it might be yeah, it doesn't matter, it is just A. So we need a transition from B from left part of B to A. So did we have it? So I state that in this table we already had to have a 1 in this right table. Why is that? Because when we had this situation, yeah, we had point what? This is because I already did everything incorrectly. So this is not C01. Then we have C02 first of all. Then we have maybe B11, yeah. B10. Then only then we have B11 and then we have A. So in the fourth table we need to have 1, 1. Yeah, here it is. And from it we needed to go to there. Okay, for now let's forget about it. Okay, let's look at the lower thing. So we have C00, C01, C02, again B10, B11. Ah, actually they are the same. No, they are not the same. They are not the same. This is two different things. This is two different things. So actually I needed to get to B11 two different ways from B10. So B10 is still the same, but I needed to go to B11 two different ways. Not to... what? No, to B11 not two different ways, but to A two different ways. Yeah, so let me show you. We have some B situation. So we have several optimal segments. And we have, for example, something here and something here. So if we pair up with this, we actually lose. Yeah, because it is much greater than this. So it says that AKL plus equals BKL plus 1 times L plus 1. Okay, understandable. But also, when we pair up with this thing, we also win C, K plus 1 L times K. Because, again, we're... ah, no. No, what? Ah, I see. It is not immediately a win. Yeah, it is not immediately a win. Okay, here we have A, definitely. Then A. But here, after B11, yeah, this closes. This closes. So after we do it, what do we have? We have a problem. I think we have a problem here. We have a problem here because so we have an optimal segment. We have here an active point. However, it is not used by our greedy algorithm. So the greedy algorithm does not use any of these active points. So we need one more dimension. Actually, is it true that we always lose in this case? So which case do I mean? I mean that I just mean this beginning. I mean this beginning. I think that actually no. It does not mean that we immediately lose, because we can have something like this. Blue, blue, green, green. Here we have black, but before the end we also have red, red. Yeah, in this case, the optimal answer is to take 2 blues and 2 reds. But the greedy answer is also take 2 blues and 2 reds. We just need one more thing. For example, D, I, K, L, which says that the greedy algorithm does not have a current point. Well, it's strange that we here cannot get to A from C. Our algorithm disallows getting from A to C. And this is strange because it should be possible. Yeah, like we have something like this, something like this, but also we have an active point here, and then it finishes and we get one more segment. And it is important that the greedy algorithm does not have any active points. This is what you mean. Okay, yes, I think yes. So we need one more dimension. Well, actually, we start with D00 is 1. Okay, let's recalculate this formula. So A does not change. A gets one more addend. Which addend does A get? A gets an addend when what happens? A gets an addend. A gets an addend. When what happens? Let me think. A gets an addend when we have D. Yeah, so let's assume that we have D. We just need to reconsider everything, I think. I think we need to reconsider everything. Let's start with B. So we have two optimal segments, for example, but we have one segment here and an active segment here somewhere. And active point. And also we have K points here and L points here. So an opening does not change anything. An opening simply works as it is. The closing can pair up with... So each time it pairs up with us, with the greedy algorithm, it becomes D actually. It actually becomes D. So, well, here, all this sum, I think, all this sum actually should be transferred to D. Doesn't it? I think yes. All these sums just should be transferred to D. Yeah, also this thing. Yeah, I think this thing should be transferred to D. What does it mean? It means that we have... Yeah, it should be transferred to D. No, no, I wasn't right. I broke everything. Let's fix. So these should be transferred. To D. Okay, where can we go from D? Where can we go from D? So we have a new closing segment. So if we have an opening one, we simply go to C. C? Yes, to C. So this becomes sum of get pref C and actually get pref D. Here. Also, it could be a closing segment pairing up with this one, or this one, or this one. In this case, it is still D. Nothing changes. It is still D. So product of product of get prevd k plus 1 L. So we pair up with one of these points. We form a new pair. And that's it. Also, we can pair up with this one. And unfortunately, this is A because the greedy algorithm does not have a chance. Which is bad for the greedy algorithm. So AKL. Yeah, we can add get prevd of k L plus 1. To 27. Okay, this is really bad that it is 27. This is really bad that it's 27. This is really bad. The fact that it is 27 means that I am helpless. Okay, I'm not helpless. It should be product of L plus 1 and get preved. Okay, here we go. Now we can ask for a greater something. Let's print the debug information. Okay, let's run release, of course. It is already that bad. Cubic time 400 in... Okay, it is understandable, but it is very bad. So I cannot even run this one. So 3000 is hopeless. Let's speed up it a little bit, I think. To speed up it a little bit, I think we need to stop at some point here. So we need to stop if k plus l should be what? K plus L should be at most minimum of ether and 2n minus ether. Okay, minus k. It still works. And this time it's several times faster. Okay, maybe we will get it to work for 1000, but not for 3000, of course. For 3000 it is hopeless. It is still hopeless for 3000. Let's check that it is at least giving correct answer. Memory limit on memory limit? It is n squared. Ah, it's n squared, but it still can be memory limit. How much memory do I take? What? 15 megabytes, 19 megabytes, 25 megabytes, 32 megabytes. Okay, we can optimize the memory easily. So we know that in total a plus b should be no more than n. So we can do it. Now it's twice less memory, should be. Should be twice less memory. Right? Yes, it is probably twice less memory. Now it's TL24 with twice less memory. So we now should look at this dynamic and understand if we can improve it. Yeah, so what we dislike here definitely is that it uses both K and L, and maybe we don't need both of them. However, unfortunately, it seems like we need. It seems like we need. probably I can work for this number, but not for bigger. Right? Okay, for now it sounds hopeless, unfortunately. So maybe next time. Thank you for watching. Bye.